What if everything we thought we knew about the size of the universe was wrong? Right now, at this very moment, the James Webb Space Telescope is staring deeper into space than any instrument in human history. And what it's finding is breaking every model, shattering every prediction, rewriting every textbook, 100,000 galaxies. Mapped in stunning detail, galaxies that shouldn't exist. Galaxies so massive, so ancient, so impossibly bright, that they're forcing scientists to question the fundamental laws of physics. The universe isn't just bigger than we thought, it's bigger than we ever imagined possible. And the implications? They're mind-bending. Some of these galaxies formed just 200 million years after the Big Bang. That's like finding a fully grown adult human 5 minutes after conception. It shouldn't be possible. The math doesn't work. The timeline doesn't add up. Yet, there they are, shining in Webb's infrared eyes. Ancient Titan galaxies that challenge everything we know about cosmic evolution. Hit that subscribe button if you want to fall asleep to the universe's deepest revelations. We're exploring cosmic mysteries every week that will blow your mind while calming your thoughts. Trust me, after tonight, you'll never look at the night sky the same way again. Let's dive into the cosmic deep. Chatutuanpan, December 2022 changed everything. NASA released the James Webb Space Telescope's first deep field image, a patch of sky so small it would be covered by a grain of sand held at arm's length. In that impossibly tiny slice of cosmos, Webb found something that made astronomers around the world stop breathing. Thousands upon thousands of galaxies. Not just any galaxies. Ancient ones. Primordial structures from the universe's infancy. Galaxies shining with light that had been traveling for over 13 billion years before reaching Webb's golden mirrors. But that was just the beginning. Over the following months, as Webb continued its systematic survey of the deep universe, the numbers kept climbing. Tens of thousands of galaxies, hundreds of thousands, each observation peeling back another layer of cosmic history. By late 2024, the count had reached something extraordinary. Over 800,000 galaxies mapped in unprecedented detail. To understand what this means, you need to grasp how Webb sees the universe differently than anything before it. Hubble, the legendary space telescope that preceded Webb, observed primarily invisible light, the same wavelengths our eyes detect. When Hubble looked at distant galaxies, it saw them as they appeared billions of years ago, their light stretched into reddish hues by the universe's expansion. But there was a limit. Beyond a certain distance, beyond a certain age, galaxies became too faint, too red-shifted for Hubble to detect clearly. That's where Webb comes in. Webb doesn't see invisible light. It sees in infrared, wavelengths longer than red, invisible to human eyes but perfect for detecting the most ancient light in the cosmos. As the universe expands, light from the earliest galaxies gets stretched so much that it shifts entirely out of the visible spectrum and into the infrared. For those ancient photons, Webb is the only eye that can see them. The telescope itself is a marvel of engineering, a primary mirror 6.5 meters across, made of 18 hexagonal segments coated in a microscopically thin layer of gold. It orbits the Sun at a location called L2, Lagrange Point 2, about 1.5 million kilometers from Earth, where it maintains a stable position relative to Earth and Sun. At that distance, shielded from the Sun's heat by a tennis court-sized sun shield. Webb's instruments cool to just above absolute zero. That extreme cold is essential. To detect the faint infrared glow of the universe's first galaxies, Webb's detectors must be colder than the objects they're observing. And they are. The mid-infrared instrument operates at -266 degrees Celsius. At that temperature, thermal noise nearly vanishes, allowing Webb to detect photons from galaxies so distant, so ancient, that they existed when the universe was less than 3% of its current age. The 800,000 galaxies Webb has mapped come from multiple deep field surveys. The Cosmic Evolution, Early Release, Science Survey, SEERS, the JWST Advanced Deep Extragalactic Survey, JADES, the Prime Extragalactic Areas for Rayonization and Lensing Science, PEARLS. Each survey targeted different regions of sky, using different instrument combinations, looking for different types of objects. But together, they've created the most comprehensive map of the deep universe ever assembled. And what that map reveals is staggering. Galaxies at redshift 10, 12, 14, meaning we're seeing them as they existed when the universe was between 200 and 400 million years old. For comparison, the universe is now 13.8 billion years old. We're looking at infant galaxies, cosmic toddlers, structures that formed in the cosmic dawn. But here's what's breaking the models. These infant galaxies aren't small. Traditional cosmological theory predicted that the first galaxies should be tiny, dim, irregular structures, clumps of stars and gas slowly merging and growing over billions of years. The massive elliptical and spiral galaxies we see in the modern universe should have taken eons to assemble. Webb is seeing something different. Some of these high redshift galaxies are massive, shockingly massive. Galaxies containing billions of stars, appearing just a few 100 million years after the Big Bang. Galaxies that, according to our models, shouldn't have had time to form. One galaxy, designated JADES GS Z1420, appears as it was just 290 million years after the Big Bang. Spectroscopic analysis suggests it contains hundreds of millions of stars. The light from this galaxy is exceptionally bright, far brighter than models predicted for such an early epoch. Another, nicknamed Maisie's Galaxy, after the astronomer's daughter, who was born around the time of its discovery, shines from when the universe was approximately 390 million years old. It's compact but luminous, suggesting intense star formation happening at a rate that challenges theoretical predictions. And these aren't outliers. They're part of a pattern. Across Webb's deep surveys, astronomers are finding an abundance of bright, massive galaxies at high redshifts. The statistical distribution doesn't match predictions. There are too many of them. They're too bright. They formed too early. Something is wrong with our understanding of how galaxies form. Or something is wrong with our understanding of the universe itself. Dr. Ivo Labbé, from Swinburne University of Technology, analyzing Webb's data, put it bluntly. If these galaxies are as massive as they appear, we have a serious problem with our model of the universe. The problem is this: galaxies form from dark matter halos, invisible scaffolding of dark matter that pulls in gas, which then condenses to form stars. The growth of these halos is governed by the expansion rate of the universe and the density of dark matter. We know these parameters fairly well from observations of the cosmic microwave background and the large-scale structure of the universe. Given those constraints, there's a limit to how quickly dark matter halos can grow, and thus a limit to how quickly galaxies can assemble. Webb is seeing galaxies that exceed those limits. It's as if the universe had a head start we didn't know about, or as if the rules of galaxy formation were different in the early universe than they are now. Scientists are scrambling to explain it. Maybe the initial mass function, the distribution of stellar masses when stars form, was different in the early universe, creating more massive stars that shine brighter. Maybe early black holes grew faster than expected, contributing additional light. Maybe dark matter behaves differently on small scales than we assumed, or maybe, and this is the possibility that keeps cosmologists awake at night, maybe our fundamental model of the universe is incomplete. But to understand just how shocking these discoveries are, we need to journey back to the beginning, to the cosmic dark ages. when the universe went dark and waited for the first stars to ignite. For the first 380,000 years after the Big Bang, the universe was opaque. Not dark, opaque. There's a difference. The universe was filled with light, blazing hot plasma, photons scattering off free electrons in every direction. But that light couldn't travel far. It was trapped, bouncing endlessly between particles in an infinite cosmic fog. Then, as the universe expanded and cooled, something changed. The temperature dropped below about 3,000 Kelvin, cool enough for electrons and protons to combine and form neutral hydrogen atoms. This moment, called recombination, freed the photons. Suddenly, light could travel unimpeded across space. That's the light we see today as the cosmic microwave background. The afterglow of the Big Bang, stretched by 13.8 billion years of expansion into microwave wavelengths. But after that flash of liberation, the universe went dark, truly dark. No stars existed yet. No galaxies, just neutral hydrogen gas, slowly clumping together under gravity's pull, forming denser and denser clouds in the gravitational wells carved out by dark matter. This period, from about 380,000 years to perhaps 100 or 200 million years after the Big Bang, is called the Cosmic Dark Ages, and it's one of the least understood epochs in cosmic history. We can't observe it directly. No light was being produced. No stars had ignited. The universe was a vast, dark expanse of hydrogen gas, structure forming invisibly in the void. Then, sometime around 100 to 200 million years after the Big Bang, the first stars turned on. These weren't stars like our sun. They were monsters. Population 3 stars, formed from primordial hydrogen and helium with almost no heavy elements. Without heavy elements to help cool the gas clouds, these first clouds collapsed into incredibly massive stars, perhaps 100 to 1,000 times the mass of our sun. When they ignited, they blazed with ultraviolet fury. That ultraviolet radiation did something crucial. It began reionizing the universe. The UV photons from the first stars had enough energy to strip electrons away from hydrogen atoms, turning neutral hydrogen back into ionized plasma. But this time, the universe was much larger, much more diffuse. The ionized bubbles around early stars didn't recombine immediately. They expanded, growing larger as more stars formed, until eventually the bubbles overlapped and merged. By about 1 billion years after the Big Bang, the process was complete. The entire universe had been reionized. It's been transparent ever since, which is why we can see distant galaxies at all. This epoch of reionization is critical to understanding galaxy formation. The first stars and galaxies created the ionized universe we inhabit. Their radiation reshaped the cosmos, clearing the fog and allowing structure to grow. Webb was designed, in part, to probe this era, to find the sources of reionization, to detect the first galaxies and understand how they transformed the universe. And what it's finding is rewriting the timeline. Many of the 800,000 galaxies Webb has mapped fall into this critical reionization era. Galaxies at redshift 6 to 15, corresponding to when the universe was between 200 million and 1 billion years old. These galaxies show clear spectroscopic signatures of ionized gas. Their light contains emission lines from oxygen, hydrogen, and other elements, evidence of intense star formation and energetic radiation. But the surprise is how organized they already are. Traditional models suggested that reionization-era galaxies would be chaotic, irregular blobs of stars and gas, still in the process of assembly. Mergers should be common. Structure should be minimal. Yet Webb is seeing galaxies with clear morphologies, spiral structures, central bulges, organized disk-like forms. One galaxy at redshift 8.2 shows what appears to be a bar, a linear structure of stars across its center, similar to the Milky Way's bar. Bars form through gravitational instabilities in rotating disks. They require time to develop, time for the disk to settle, for orbits to organize, for resonances to amplify the instability. Finding: a bar in a galaxy just 600 million years after the Big Bang suggests that galaxy disks were forming and stabilizing much faster than models predicted. The metallicity, the abundance of elements heavier than hydrogen and helium, is another puzzle. First generation of stars, population 3, should contain essentially zero heavy elements. They form from primordial gas. When they explode as supernovae, they enrich the surrounding gas with the heavy elements forged in their cores. The second generation, population 2, forms from this enriched gas and contains some heavy elements. Subsequent generations contain more and more, building up the periodic table over cosmic time. Webb is detecting oxygen emission lines in galaxies at redshift 10 and beyond. Oxygen is produced in massive stars and dispersed by supernovae. Finding it at these early epochs means that massive stars had already formed, lived their brief lives, and exploded, all within the first few 100 million years. That's faster than expected, much faster. One study analyzing Webb data from the JD's survey found galaxies at redshift 9 to 11 with oxygen to hydrogen ratios about 10% of what we see in the Sun. That might sound low, but remember, the Sun formed 4.6 billion years ago, after billions of years of chemical enrichment. These early galaxies achieved significant enrichment in a fraction of the time. The implications are profound. If heavy elements appeared this quickly, then the first generation of stars must have formed very early, possibly as early as 50 to 100 million years after the Big Bang. They must have been massive, living and dying in just a few million years, and their supernovae must have been extraordinarily efficient at dispersing metals into the surrounding gas. All of this points to an early universe that was more active, more violent, more productive than we imagined. The cosmic dark ages might have been shorter than we thought. The epoch of ionization might have begun earlier, and the first galaxies might have assembled with shocking speed. Webb's 800,000 galaxies are showing us a universe in fast forward, a cosmos that raced through its infancy, eager to light up, eager to build structure, eager to become the grand cosmic web we see today. But why? What drove this rapid assembly? That's the question keeping cosmologists up at night, and the answers they're proposing are stranger than anyone expected. To understand what might have accelerated galaxy formation, we need to look at the invisible scaffolding of the universe, the dark matter halos that govern where and when galaxies can form. Galaxies don't form in empty space. They form inside halos, vast, invisible structures made of dark matter. Dark matter doesn't emit light, doesn't interact with electromagnetic radiation, can't be seen directly, but it has mass, and mass means gravity. After the Big Bang, tiny fluctuations in the density of dark matter began to grow. Slightly denser regions pulled in more dark matter through gravity. Those regions became denser still, attracting even more matter. Over millions of years, this process created a cosmic web, a network of dark matter filaments connecting dense nodes where galaxies would eventually form. The process is called hierarchical structure formation. Small halos form first, then merge to create larger halos. Larger halos merge to create even larger ones. It's bottom-up assembly, small structures combining into bigger structures over cosmic time. This model has been spectacularly successful at explaining the large-scale structure of the universe we observe today. Computer simulations based on dark matter physics reproduce the cosmic web with stunning accuracy. But here's the problem. Hierarchical formation takes time. Dark matter halos grow at a rate determined by the density and distribution of dark matter in the early universe. We know these parameters from observations of the cosmic microwave background. Given those constraints, simulations predict how massive dark matter halos could have grown by any given time after the Big Bang. And those predictions don't match what Webb is seeing. The massive galaxies Webb is detecting at high redshift would require correspondingly massive dark matter halos to host them. But according to the Standard Model, those halos shouldn't exist yet at those epochs. Let's break down the numbers. A galaxy containing 1 billion solar masses of stars needs a dark matter halo of at least 10 billion solar masses to form in. That's the minimum ratio between stellar mass and halo mass in standard galaxy formation theory. Webb is finding galaxies with estimated stellar masses of 1 to 10 billion solar masses at redshift 10 to 14, when the universe was 200 to 450 million years old. Running the simulations backward to create halos massive enough to host these galaxies by those epochs, the initial density fluctuations would need to be much larger than what we observe in the cosmic microwave background. There's a mismatch, a fundamental tension between what the early universe looked like, as seen in the CMB, and what the later universe looks like, as seen by Webb. Several explanations are being explored. One possibility: maybe dark matter behaves differently on small scales than we assumed. Most dark matter models assume it's cold, meaning the particles move slowly compared to the speed of light. Cold dark matter clumps efficiently on all scales. But what if dark matter has additional interactions we haven't accounted for? What if it can self-interact, colliding and exchanging energy in ways that affect halo growth? Such interactions could potentially accelerate the collapse of halos in the early universe. This is speculative. There's no direct evidence for interacting dark matter, but it's a possibility being actively researched. Another explanation: maybe the initial density fluctuations weren't uniform. The Standard Model assumes that density fluctuations follow a specific statistical distribution, nearly scale invariant, with similar amplitudes on all size scales. This assumption is based on inflation theory, which predicts that quantum fluctuations in the early universe were stretched to cosmic scales. But what if there were additional fluctuations on small scales? What if some regions had higher than average density contrasts, creating seeds for rapid halo growth? Some inflationary models predict exactly this: enhanced small-scale fluctuations from specific inflationary dynamics. If those fluctuations existed, they could produce an overabundance of massive halos in the early universe without violating CMB observations, which are sensitive primarily to large-scale fluctuations. A third explanation involves primordial black holes. What if a small fraction of dark matter isn't made of exotic particles, but of black holes formed in the very early universe, microseconds after the Big Bang? These primordial black holes could act as seeds, attracting dark matter and gas much more efficiently than diffuse dark matter halos. A galaxy forming around a primordial black hole could assemble faster than one forming from scratch. The black hole provides a pre-existing gravitational well, jump-starting the process. This is more than speculation. Some Webb observations hint at active galactic nuclei, supermassive black holes, at the centers of high-redshift galaxies. If those black holes are primordial in origin, they could help explain the rapid assembly. But perhaps the most radical explanation is that our cosmological model itself is incomplete. The Standard Model, called lambda CDM, includes dark energy, lambda, and cold dark matter, CDM, plus ordinary matter and radiation. It's been tested extensively and matches most observations, but it makes assumptions. It assumes general relativity holds on all scales. It assumes the expansion rate of the universe is governed by the Friedmann equations. It assumes dark energy is a cosmological constant with a fixed density. What if one of those assumptions is wrong? What if gravity behaves differently on cosmological scales than general relativity predicts? Modified gravity theories like MOND, modified Newtonian dynamics, or FR gravity could potentially alter the growth rate of structure in the early universe. Or what if dark energy isn't constant? What if it was different in the early universe? Perhaps weaker, allowing gravity to work more efficiently, pulling matter together faster. These are deep questions, challenging fundamental physics, and they're being taken seriously because the observations demand it. Dr. Mike Boylan Colchin from the University of Texas, analyzing Webb's high redshift galaxy discoveries, wrote a paper titled Stress Testing Lambda CDM with High Redshift Galaxy Candidates. His conclusion: the galaxies are so extreme that they create significant tension with the standard model. Tension is academic speak for something's broken, either. The galaxies aren't as massive as they appear. Perhaps dust or emission lines are fooling us into overestimating their stellar masses. Or the cosmological model needs adjustment. Follow-up observations are crucial. Webb is conducting detailed spectroscopy on the most extreme candidates, measuring their masses more precisely, checking for alternative explanations. But with each new observation, the tension grows. The 800,000 galaxies in Webb's surveys include hundreds of high redshift candidates. Some will be confirmed, others may turn out to be foreground objects or misidentified. But even if half are real, even if only a fraction are as massive as initial estimates suggest, the problem remains. The universe is producing massive galaxies too quickly. And that means something fundamental about cosmic evolution, about dark matter, about structure formation, about the expansion of the universe itself, is not what we thought. But dark matter isn't the only puzzle. There's another cosmic mystery hidden in Webb's data, one involving the first black holes and how they grew to monstrous sizes impossibly fast. At the center of most galaxies sits a supermassive black hole. The Milky Way's central black hole, Sagittarius A, contains about 4 million solar masses. That's enormous, but it's actually small compared to the monsters lurking in other galaxies. M87, the giant elliptical galaxy famous for the first direct image of a black hole, hosts a beast of 6.5 billion solar masses. Some quasars contain black holes exceeding 10 billion solar masses. These are supermassive black holes, a different class from stellar mass black holes formed when massive stars collapse. Where did they come from? How did they grow so large? The standard formation scenario goes like this. In the early universe, the first massive stars collapsed into black holes of perhaps 10 to 100 solar masses. These seed black holes grew by accreting gas from their surroundings and by merging with other black holes when galaxies collided. Over billions of years, through countless meals of gas and mergers, these seeds grew into the supermassive black holes we see today. That's the theory. And it works well for most black holes in the nearby universe. But Webb is finding black holes that break this model. Quasars, intensely bright objects powered by gas spiraling into supermassive black holes, have been detected at redshift 7, 8, even above 10. These are quasars, shining when the universe was less than 700 million years old. The black holes powering them contain hundreds of millions to billions of solar masses. That shouldn't be possible. Not in the time available. Black holes grow by accretion, pulling in gas and converting it to energy and mass. But there's a limit to how fast they can grow, called the Eddington limit. When gas falls toward a black hole, it heats up and emits radiation. That radiation pushes outward against infalling material. If the accretion rate gets too high, the outward radiation pressure becomes so strong that it blows away the infalling gas, shutting down the accretion. The Eddington limit sets the maximum growth rate. A black hole can roughly double its mass every 50 million years if it's accreting at the Eddington limit. continuously. Let's do the math. Start with a 100 solar mass seed black hole formed 100 million years after the Big Bang. Accrete at the Eddington. Limit for 500 million years. By 600 million years after the Big Bang, you'd have a black hole of roughly 3,000 solar masses. Not 3 million. 3,000. To reach a billion solar masses by that time, you'd need to exceed the Eddington limit by factors of hundreds. Or you'd need to start with a much more massive seed, thousands or tens of thousands of solar masses. Neither option fits comfortably with standard astrophysics. Can black holes exceed the Eddington limit? In theory, yes, if the accretion is very efficient, or if the geometry is such that radiation doesn't escape easily. Some models invoke dense, dusty environments that trap radiation, allowing super-Eddington accretion, but sustaining that for hundreds of millions of years seems implausible. The alternative is massive seeds instead of black holes, forming from the collapse of individual massive stars. Perhaps they formed from the direct collapse of primordial gas clouds. If a massive cloud, 10,000 to 100,000 solar masses, collapsed directly into a black hole without fragmenting into stars first, you'd have a heavy seed black hole. With a head start like that, reaching a billion solar masses by 600 million years becomes possible. But direct collapse requires special conditions. The gas must be extremely hot to prevent fragmentation and metal-free. Heavy elements cause cooling, which leads to fragmentation. Strong ultraviolet radiation from nearby star-forming regions can heat the gas, but that radiation must come from somewhere, from stars that formed earlier. It's a chicken-and-egg problem. You need early star formation to create the conditions for direct collapse, but direct collapse is supposed to explain the early black holes. Webb's observations are adding new data to this puzzle. One quasar, designated J0313-1806, appears at redshift 7.64, when the universe was just 670 million years old. Its black hole is estimated at 1.6 billion solar masses. Spectroscopic observations from Webb confirm it's a genuine high redshift quasar, not a foreground object. And detailed analysis of the light shows the black hole is accreting at a very high rate, possibly super-Eddington. Even more extreme is Sears 1670, a galaxy detected at redshift 14.2, just 290 million years after the Big Bang. While not confirmed as a quasar, it shows signs of an active galactic nucleus, suggesting a massive black hole is already present. If confirmed, this would push the black hole seed formation back to extraordinarily early times. Researchers are now seriously considering alternatives to the standard black hole formation. Picture? One idea: primordial black holes. These hypothetical objects would have formed in the first moments after the Big Bang, from density fluctuations in the hot, dense plasma. If they exist, they could provide ready-made massive seeds scattered throughout the early universe. Another idea: runaway collapse in the densest dark matter halos. Perhaps in the most extreme environments, dark matter density was high enough to catalyze the direct collapse of gas into massive black holes through mechanisms we don't yet fully understand. A third idea: black hole mergers happened much more frequently in the early universe than we assumed. If small black holes were merging constantly in the dense environments of early galaxies, they could grow faster than accretion alone would allow. Each explanation has problems. Primordial black holes are unproven. Runaway collapse lacks detailed modeling. Frequent mergers require unrealistically high black hole densities. Yet the observations demand an explanation. Dr. Xiaohui Fan from the University of Arizona, a leading expert on high redshift quasars, puts it simply: these black holes are telling us that something happened very early in the universe that we don't understand. The 800,000 Galaxies mapped by Webb include thousands, showing evidence of active galactic nuclei, supermassive, black holes feeding on surrounding gas. Many are at high redshift, adding to the population of early massive black holes that challenge formation theories, and it's not just their existence that's puzzling, it's their relationship to their host, galaxies. Because what Webb is discovering is that these early black holes weren't just growing, they were building the galaxies around them. In the modern universe, there's a relationship between galaxies and their central black holes. Bigger galaxies have bigger black holes. The correlation is tight. The mass of a galaxy's central black hole is roughly proportional to the mass of its bulge, the dense central region of stars. This relationship suggests that galaxies and black holes grow together, their evolution intertwined through cosmic history. But which came first? Did galaxies form and then create black holes? Or did black holes form first and trigger galaxy formation around them? Webb's observations of the early universe are suggesting something radical. In the cosmic dawn, black holes may have come first. The mechanism is called feedback, but not the gentle kind. This is violent, transformative feedback that reshapes entire galaxies. Here's how it works. A massive black hole forms in the early universe through one of the mechanisms we discussed, perhaps direct collapse, perhaps primordial origins. This black hole sits in a dense region of dark matter and gas. It begins accreting. Gas spirals inward, forming an accretion disk. As the gas nears the black hole, it heats to millions of degrees, emitting intense radiation across the electromagnetic spectrum. X-rays, ultraviolet, visible light. This radiation doesn't just escape into space, it slams into the surrounding gas clouds, ionizing atoms, heating the gas to tens of thousands of degrees. Normally, gas needs to cool to form stars. Hot gas resists collapse. So, ironically, the black hole's radiation can suppress star formation in its immediate vicinity. But further out, something different happens. The radiation creates shock waves, pressure waves propagating through the gas. These shocks compress the gas in certain regions, triggering instabilities that lead to runaway collapse. Stars form, lots of them, all at once. It's called positive feedback, the black hole's activity triggering star formation rather than suppressing it. At the same time, the black hole can drive powerful jets, beams of plasma and magnetic fields shooting outward at near-light speeds. When these jets slam into surrounding gas, they create enormous bubbles of hot, shocked gas. These bubbles push gas around, clearing out the central regions but compressing gas at larger radii. Again, this compression can trigger star formation. The result? A burst of star formation, orchestrated by the black hole, building up the stellar mass of the galaxy. Webb is seeing evidence of this process in action. High redshift galaxies with active black holes show peculiar characteristics. Their star formation rates are extremely high, sometimes forming hundreds of solar masses worth of stars per year. For comparison, the Milky Way forms about 1 solar mass of stars per year. Spectroscopic observations reveal broad emission lines, signatures, of gas moving at high speeds near the black hole. But they also show narrower emission lines from star-forming regions throughout the galaxy, indicating that while the black hole is active, stars are forming vigorously. One galaxy, EGSY 8P7, at redshift 8.68, shows exactly this pattern. A bright, central source, likely an active black hole, surrounded by regions of intense star formation. The galaxy is compact, just a few thousand light-years across, but it's building stars at a prodigious rate. The total stellar mass of the galaxy suggests it has been forming stars for at least 100 million years. but the black hole appears to be only recently active. This timeline supports the idea that the black hole turned on and triggered a new wave of star formation. Another example is GN-Z11, one of the most distant galaxies confirmed by Webb at redshift 10.6. This galaxy is exceptionally luminous for its epoch, so bright that it was initially thought to be a foreground object. Detailed spectroscopy reveals a compact core with a UV-bright component consistent with an active galactic nucleus. Surrounding this core is a more extended region of star formation. The spatial distribution suggests that the black hole is at the center, driving feedback that affects the entire galaxy. Modeling indicates that the black hole's mass is a surprisingly high fraction of the total stellar mass, much higher than the ratio seen in local galaxies. This supports the idea that in the early universe, black holes grew faster than their host galaxies, achieving disproportionate masses. Over time, as galaxies continued to grow through mergers and accretion, the ratio shifted to the values we observe today. But there's a darker side to black hole feedback. While feedback can trigger star formation, it can also quench it, shutting down star formation entirely and turning a vibrant, star-forming galaxy into a red and dead elliptical. This happens when feedback becomes too energetic. Instead of gently compressing gas to trigger collapse, the black hole's jets and radiation blow the gas out of the galaxy entirely. Without gas, no new stars can form. The galaxy's existing stars age and redden, and the galaxy becomes quiescent. In the nearby universe, we see plenty of quiescent galaxies, massive ellipticals with little to no star formation. The standard model suggests they were quenched by black hole feedback over billions of years, but Webb is finding quiescent galaxies. At high redshift, galaxies that appear red and dead when the universe was less than 1 billion years old. This is shocking. It means some galaxies completed their star formation, grew massive, and then were quenched, all within the first billion years. One example is Gides GSZ7 J1QU, a massive galaxy at redshift 7.3. Spectroscopy shows no emission lines from ionized gas, no sign of active star formation. The light is dominated by older stars, suggesting star formation ceased at least 100 million years earlier. How did this galaxy form all its stars and then shut down so quickly? Black hole feedback is the leading explanation. A massive black hole, accreting vigorously, could have expelled all the gas, quenching star formation. But this raises new questions. If black holes can quench galaxies this early, why didn't all early galaxies get quenched? Why do we see both star-forming and quiescent galaxies at high redshift? The answer likely involves the details of feedback. The mass of the black hole, the density of surrounding gas, the presence of inflows and outflows, the magnetic field configuration. These factors determine whether feedback is positive, triggering star formation, or negative, quenching it. Webb's 800,000 galaxies include examples across this spectrum. Star-bursting galaxies with active black holes. Quiescent galaxies with signs of recent quenching. Galaxies in transition, caught in the act of shutting down. By studying the statistical distribution, how many galaxies are in each category at each cosmic epoch, astronomers can constrain the physics of feedback and understand how black holes shaped galaxy evolution. What's emerging is a picture where black holes aren't just passengers in galaxies, they're architects. In the early universe, when gas was abundant and dense, black holes may have been the primary drivers of galaxy assembly. They pulled in gas, triggered star formation through feedback, and regulated when and how galaxies grew. Over cosmic time, as the universe expanded and gas became more diffuse, this relationship changed. Galaxies began to grow more through mergers than through in situ star formation. Black holes became less dominant, though they still played a regulatory role. But in those first billion years, black holes ruled. And here's the truly mind-bending implication. If black holes came first and built galaxies around them, then the universe's structure, the cosmic web of galaxies we see today, may have been seeded by black holes. Not by dark matter alone, not by random density fluctuations, but by black holes, creating islands of star formation in the cosmic dawn, each one growing into a galaxy. It's a radical revision of the cosmic origin story, and it's being written in the light from 800,000 galaxies, captured by Webb's golden mirrors. But there's another mystery in this light, something even stranger. Some of these early galaxies are glowing in ways that shouldn't be possible, emitting light from elements that shouldn't exist yet. Every element in the periodic table has an origin story. Hydrogen and helium were born in the Big Bang. Lithium, too, in tiny amounts. Those three elements made up essentially 100% of the universe's normal matter for the first few 100 million years. Everything else, carbon, oxygen, nitrogen, iron, gold, was forged later. In stars are nuclear furnaces. In their cores, hydrogen fuses to helium, releasing energy. As stars age, they fuse helium into carbon, carbon into oxygen, and so on up the periodic table. Massive stars can create elements all the way to iron. Beyond iron, elements form in supernova explosions, the violent deaths of massive stars, or in neutron star collisions. When these stars explode, they scatter their heavy elements into space. This enriched gas then collapses to form new stars, which contain a higher fraction of heavy elements. Over cosmic time, generation after generation, the universe's metallicity, its abundance of heavy elements, increases. This process takes time. Lots of time. The first stars, population 3, should be pure hydrogen and helium. The second generation, population 2, should have low but non-zero metallicity. Only after many cycles of star birth, death, and enrichment should you get population-wise stars like our Sun, with 1 to 2% heavy elements by mass. That's the theory. Webb is seeing something different. Spectroscopic observations of high-redshift galaxies are revealing emission lines from heavy elements: oxygen, neon, nitrogen, even iron, in galaxies just a few 100 million years after the Big Bang. The abundances are lower than in modern galaxies, yes, but they're higher than models predict for such early times. One galaxy at redshift 13.2, designated JADES GS Z13 Fernaro, shows clear oxygen emission lines. Oxygen is produced in massive stars and expelled by supernovae. Detecting it means massive stars had already formed, lived their short lives, a few million years, and exploded, all within about 320 million years after the Big Bang. That's tight. Very tight. Models of early chemical enrichment suggest the first stars formed around 100–200 million years after the Big Bang. If they were very massive, 100+ solar masses, they'd live only 2 to 3 million years before going supernova. But even in the best-case scenario, you'd need multiple generations of stars to build up detectable oxygen abundances. First-generation supernovae produce some oxygen. That enriched gas forms second-generation stars, which produce more oxygen. Maybe a third generation is needed before the abundance is high enough to see in spectra. Each generation takes tens of millions of years to form, live, and die. The timeline is barely possible, but it requires everything to happen at maximum speed. Star formation must begin extremely early, stars must be very massive, and enrichment must be very efficient. Webb is suggesting that's exactly what happened. But there's a twist. Some galaxies show unexpectedly high ratios of nitrogen to oxygen. In typical stellar nucleosynthesis, oxygen is produced more abundantly than nitrogen. Oxygen comes from massive stars on short timescales. Nitrogen comes from intermediate mass stars on longer timescales. So the nitrogen to oxygen ratio is a cosmic clock. It tells you how long star formation has been happening. Low NO means young stellar populations. High NO means older populations. Some of Webb's high redshift galaxies show NO ratios higher than expected for their age. It's as if they've been forming stars for longer than the age of the universe at that redshift. That's impossible, unless the enrichment process is fundamentally different in the early universe. One possibility: the initial mass function, the distribution of stellar masses at birth, was different. In the local universe, most stars are low mass. For every massive star, there are thousands of sun-like stars and millions of red dwarfs. This distribution is called the IMF, initial mass function. But perhaps in the early universe, with no heavy elements to help gas clouds fragment. The IMF was top-heavy. Maybe most stars were massive. A top-heavy IMF would produce more supernovae per unit stellar mass, enriching the gas faster. It could also shift the relative abundances of elements, potentially explaining the high NO ratios. Another possibility: supernova yields, the amount of each element a supernova produces, were different. Supernova nucleosynthesis depends on the star's mass, rotation, and metallicity. The first supernova, from zero metallicity stars, might have had different yields than modern supernovae. If primordial supernova produced more nitrogen relative to oxygen than modern ones, it could explain the observations. A third, more exotic possibility: enrichment from population 3 stars happened earlier than we think. What if the very first stars formed not at 100 to 200 million years, but at 50 million years, or even earlier? Some models suggest that in the densest dark matter, halos, gas could have cooled and collapsed very rapidly, forming stars within tens of millions of years of the Big Bang. If true, you'd have an extra 50–100 million years for chemical enrichment. Enough time for multiple generations of stars to cycle through, building up heavy elements. But this requires the first dark matter halos to form earlier and denser than standard models predict. Which brings us back to the dark matter problem. Everything connects. The massive early galaxies, the rapid black hole growth, the unexpectedly high metallicity. They all point to an early universe that was more active, more extreme, more productive than models allow. Webb's spectrographs are revealing this chemistry in exquisite detail. The NIR SPEC instrument can break down the light from distant galaxies into thousands of wavelengths, revealing individual emission and absorption lines from dozens of elements. By measuring the strengths of these lines, astronomers can determine not just which elements are present, but in what quantities. This allows them to reconstruct the star formation history, the supernova rate, and the enrichment timeline of each galaxy. For the 800,000 galaxies Webb has mapped, detailed spectroscopy is available for thousands. Each spectrum is a fingerprint of that galaxy's chemical evolution. And the pattern that's emerging is clear. Early galaxies were chemically mature far earlier than expected. Carbon, oxygen, neon, the building blocks of planets and life, were present in significant quantities within the first billion years. Some of these galaxies might already have had rocky planets orbiting their stars, planets with oxygen in their atmospheres. Perhaps the timeline for cosmic complexity, for planets, for chemistry, for the potential emergence of life, may be much shorter than we thought. But to understand how common these chemically mature galaxies are, and what they mean for the universe as a whole, we need to zoom out. We need to see the big picture. the cosmic census that Webb's 800,000 galaxies reveal. Terschfeiod, 800,000 galaxies. Each one a data point. Each one a piece of the cosmic puzzle. Together, they form the most comprehensive census of the universe's evolution ever compiled. Astronomers don't study galaxies one at a time. They study populations, statistical distributions, how many galaxies of each type exist at each cosmic epoch, how galaxy properties, mass, star formation rate, metallicity, change over time. This statistical approach reveals patterns invisible in individual objects, and the patterns Webb is revealing are rewriting our understanding of cosmic history. Let's start with the galaxy mass function, the distribution of galaxy masses at different redshifts. In the nearby universe, there are many low-mass galaxies and few high-mass ones. The distribution follows a specific mathematical form called a Schechter function. It's well understood and well explained by models of hierarchical galaxy formation. Small galaxies are common because they form in small dark matter halos, which are abundant. Large galaxies are rare because they require rare, massive dark matter halos, or multiple mergers of smaller galaxies. Webb's deep surveys allow us to measure the galaxy mass function at high redshift, seeing how it evolves over cosmic time. And here's the surprise. At redshift 8 to 10, the high mass end of the distribution is much more populated than models predict. There are too many massive galaxies, not by a small margin, by factors of 3 to 10. This is the impossibly early galaxies problem, now quantified statistically. One galaxy could be an outlier, a dozen could be a fluke, but hundreds? That's a systematic discrepancy. Dr. Ivo Labé's team, analyzing JWST data from the Sears survey, found that massive galaxies at redshift 7 to 9 are about 5 times more abundant than lambda CDM predictions. They considered various explanations. Perhaps the stellar masses are overestimated. Dust or emission lines could be misleading, but even accounting for uncertainties, the excess remains. Another statistical measure is the cosmic star formation history, the rate at which the universe as a whole forms stars as a function of time. Traditionally, this history shows a peak at redshift 2 to 3, about 10–11 billion years ago, and a decline both toward the present and toward earlier times. The decline toward earlier times makes sense. Fewer galaxies existed, so less star formation occurred overall. But Webb is showing that the decline at high redshift is less steep than expected. Star formation in the early universe was more vigorous than models predicted. Integrating the star formation rate over time gives the cosmic stellar mass density, the total mass locked up in stars at each epoch. Webb's data suggests that by redshift 8, 600 million years after the Big Bang, about 10 to 6 to 10·7 solar masses per cubic megaparsec were already in stars. Models predicted about 10^5, a factor of 10^100, lower. This means the universe was building stars faster, earlier, and more efficiently than we thought. Why? One possibility is that the star formation efficiency, the fraction of available gas that gets converted into stars, was higher in the early universe. Normally, only about 10% of the gas in a galaxy becomes stars. The rest is ejected by supernova feedback or remains unconverted. But perhaps in the early universe, with denser gas and less heavy element cooling, star formation was more efficient. Maybe 20% or 30% of gas turned into stars. Higher efficiency would produce more stars from the same amount of gas, increasing the cosmic stellar mass density without requiring more dark matter halos. Another possibility is that gas infall rates were higher. Galaxies grow by accreting gas from the intergalactic medium. The rate of this infall depends on the density of the universe and the depth of the gravitational potential wells if early dark matter halos were more efficient at pulling in gas, perhaps because the intergalactic medium was denser, or because feedback was less effective at preventing infell, then galaxies could have grown faster. A third possibility involves the initial mass function again. If early stars were predominantly massive, they'd produce more light per unit mass. This could make early galaxies appear more massive than they actually are. But this doesn't fully solve the problem, because spectroscopic observations constrain the stellar populations. You can't hide low-mass stars indefinitely. They leave signatures in the spectrum. The statistical analysis also reveals something else: diversity. Not all high-redshift galaxies are the same. Some are compact and red, quiescent early-type galaxies. Others are blue and star-forming. Some have active black holes. Others don't. This diversity suggests that galaxy evolution in the early universe wasn't uniform. Different environments, different histories, different outcomes. Some regions of the universe experienced early bursts of star formation, forming massive galaxies quickly, then quenching. Other regions had more prolonged star formation, building mass gradually. The cosmic web, the large-scale structure of dark matter filaments and nodes, likely played a role. Galaxies in dense nodes, protoclusters, might have evolved differently than galaxies in filaments or voids. Webb is starting to map this structure at high redshift. One survey, called Cosmos Webb, covers 0.54 square degrees, a large area by deep field standards. It's designed to find not just individual galaxies, but their environments. Early results show filamentary structures at redshift 6 to 7, chains of galaxies connected by dark matter filaments, just like in the local universe. This suggests that large-scale structure assembled earlier than expected. The cosmic web was already in place, just 1 billion years after the Big Bang. And within that web, some of the densest regions, the protoclusters, contain multiple massive galaxies in close proximity. These protoclusters are the ancestors of modern galaxy, clusters like Coma or Virgo. Seeing them at high redshift tells us when and how the largest structures in the universe formed. 1. Protocluster at redshift 7.9 contains at least 7 massive galaxies, within a region about 2 million light-years across. The total stellar mass in this region exceeds 10 billion solar masses. By comparison, a random region of space at that redshift should contain maybe 1 massive galaxy. This overdensity is a clear sign of structure, a region destined to collapse into a massive galaxy cluster by the present day. The census Webb is conducting isn't just about counting galaxies. It's about understanding the cosmic ecosystem, how galaxies, dark matter, gas, and black holes interact to build the universe we see. And that ecosystem was more complex, more active, and more mature in the early universe than anyone anticipated. But hidden in those 800,000 galaxies is perhaps the most profound implication of all, one that touches on the biggest question in cosmology. The universe is 13.8 billion years old. We know this from multiple independent measurements. The cosmic microwave background, the expansion rate, the ages of the oldest stars, they all point to the same number, give or take a few tens of millions of years. But Webb's observations are creating a problem. The massive galaxies at redshift 10 to 14 appear too evolved, too mature for their age. They contain billions of stars, significant heavy element enrichment, and well-organized structures. To build these galaxies in the time available, 300 to 500 million years, requires star formation to begin very early and proceed very efficiently, pushing the models to their limits. Maybe it's possible, barely, but there's another possibility, a more radical one. What if the universe is older than we think? Before you dismiss this as absurd, consider our age estimate comes from measuring the expansion rate and running the clock backward to when everything was together at the Big Bang. That expansion rate is called the Hubble constant. And here's the thing, we don't know it precisely. Two different methods of measuring the Hubble constant give different answers. One method uses the cosmic microwave background. By analyzing the pattern of temperature fluctuations in the CMB, cosmologists can infer the expansion rate. This gives a value around 67 kilometers SMMPC. Another method uses supernovae and other standard candles, objects with known brightness. By measuring how bright they appear at different distances, you can determine the expansion rate. This gives a value around 73 quadrants MPC. The discrepancy is about 10%. That might not sound like much, but in cosmology, it's huge. The measurements are precise enough that this difference is statistically significant. It's called the Hubble Tension, and it's one of the biggest unsolved problems in cosmology. If the true Hubble constant is lower than the CMB value suggests, the universe would be older, giving more time for early galaxies to form. A Hubble constant of 60 kilometers MPC instead of 67 would make the universe about 15.5 billion years old instead of 13.8 billion. That extra 1.7 billion years might be enough to explain the early massive galaxies, but there's no strong evidence supporting such a low Hubble constant. Both measurement methods are well tested and peer-reviewed. Some cosmologists are exploring a different possibility. What if the expansion rate was different in the early universe? The standard model assumes the expansion follows a specific history governed by the matter and energy content of the universe. Dark energy, dark matter, and ordinary matter each contribute to the expansion rate in predictable ways. But what if dark energy wasn't constant? What if it was stronger or weaker in the past? A period of accelerated expansion in the early universe, different from cosmic inflation, could alter the relationship between redshift and cosmic time. Galaxies at redshift 10 might be older than we calculate using standard cosmology. This is speculative. It requires modifying the dark energy equation of state, introducing new physics. But Webb's observations might be demanding exactly that. New physics. Another angle involves questioning the Big Bang itself. The Big Bang model is extraordinarily successful. It explains the CMB, the abundance of light elements, the expansion of space. It's been tested in countless ways and passed every test, but it's not without assumptions. It assumes general relativity holds at all scales. It assumes the universe began in a hot, dense state 13.8 billion years ago. It assumes the laws of physics have been constant throughout cosmic history. What if one of these assumptions is wrong? Some alternative cosmologies propose a cyclic universe, one that goes through repeated phases of expansion and contraction. In such a model, what we call the Big Bang might have been a bounce from a previous contracting phase. If the universe is cyclic, it could be much older than 13.8 billion years. The structures we see at high redshift might have had more time to form than the standard model allows. Again, this is speculative. Cyclic cosmology has many unresolved issues, particularly around what physics could drive a bounce. But the point is, Webb is pushing us to consider possibilities we might have dismissed before. There's also the simulation hypothesis, not in the sci-fi sense, but in a cosmological sense. What if the early universe's evolution was seeded in ways we don't understand? What if the initial conditions after inflation weren't as random as we assume? Fine-tuned initial conditions could lead to faster structure formation without changing the laws of physics. This doesn't require invoking anything supernatural, just a recognition that we don't fully understand inflation or the quantum fluctuations that seeded structure. Perhaps those fluctuations had characteristics, correlations, non-Gaussianities that enhanced structure formation on specific scales. Webb's data is being used to test these ideas. Primordial, non-Gaussianity, Deviations from purely random fluctuations would leave signatures in the distribution of galaxies. If high-redshift galaxies are more clustered than expected, it could indicate non-Gaussian initial conditions. Early results from Webb's large area surveys are looking for this clustering. The verdict is still out, but there are hints of excess clustering at redshift 6 to 8. Then there's the most conservative explanation. We're just missing something in our models. Maybe baryonic physics, the complex interactions of gas, stars, and feedback, is more complicated than we've accounted for. Current simulations of galaxy formation include prescriptions for star formation, supernova feedback, black hole growth, and feedback. But these prescriptions are simplified models, not fundamental physics. What if those simplifications break down in the early universe? What if feedback operated differently? What if star formation efficiency was higher? With better models, perhaps the observations could be explained without changing cosmology. This is the approach most astronomers favor. Extraordinary claims require extraordinary evidence. Before throwing out the Big Bang or invoking new physics, exhaust all conventional explanations. But the conventional explanations are straining under the weight of Webb's data. Every adjustment to make the models fit one observation seems to conflict with another. Increase star formation efficiency to build massive galaxies early? Now you overproduce metals and contradict the metallicity observations. Invoke top-heavy IMF to increase light output? Now you overproduce supernovae and can't explain the black hole masses. Add primordial black holes as seeds? Now you have to explain where they came from and why they have the right abundance. It's a complex, interlocking puzzle. And the more pieces Webb adds, the harder it becomes to fit them all together without changing the shape of the puzzle itself. Dr. Adam Rees, Nobel laureate and leader in measuring the Hubble constant, said, "We're seeing cracks in the cosmological model. They might just be cracks, requiring patches, or they might be signs that the whole structure needs rebuilding." Webb has only been operating for 2 years. Its full mission will last a decade or more. As more data accumulates, millions of galaxies, deeper redshifts, more detailed spectra, the picture will clarify. Either the observations will fit into an extended version of the standard model, with adjustments to baryonic physics but no fundamental changes to cosmology, or they won't. And we'll be forced to rethink the nature of the universe itself. The implications are staggering. If the universe is older, larger, or structured differently than we thought, it changes everything. Our place in the cosmos, the timeline for cosmic evolution, the potential for life elsewhere. Those 800,000 galaxies aren't just data points. They're clues in the greatest detective story humanity has ever undertaken. The story of existence itself. And as you drift toward sleep, consider this. Somewhere in that vast cosmic census, among those hundreds of thousands of distant galaxies, there might be worlds. Planets orbiting stars in galaxies billions of light years away. And on those worlds, perhaps, beings looking back toward us, wondering the same questions we ask tonight. How big is the universe? How did it begin? And what does it all mean? If this journey through cosmic space and time brought you wonder tonight, subscribe for more mysteries from the universe's edge. Every week, we explore black holes, distant worlds, and the greatest questions in science, all designed to fill your mind with awe as you drift into sleep. Sweet dreams, cosmic explorer. And remember, in a universe with 800,000 galaxies visible in a patch of sky smaller than a grain of sand, anything is possible.